Modern traffic failure stems from a coordination deficit. Our data resides in fragmented, independent optimization loops, completely blind to one another. A road segment today simultaneously functions as an autonomous vehicle operational boundary, a commercial curbside pickup zone, and an active emergency response corridor. Conventional traffic management systems try to manage this overlapping demand by optimizing isolated scalar metrics. A smart traffic light simply tries to reduce the average delay for the cars directly in front of it. In a dense physical space, optimizing one isolated subsystem actively degrades the surrounding networks. The algorithm that clears a turn lane might simultaneously block a crosswalk or force a delivery fleet into a congested detour. These misalignments trigger compounding network failures. A brief pause for a rideshare pickup creates a queue spillback, which triggers an intersection lockup, escalating into physical curbside conflicts. As long as fleets, retailers, and city infrastructure run reactive, single-objective optimizations in a vacuum, system-wide gridlock and severe crash exposure will mathematically escalate. To address this, we propose a unified topological framework, the Predictive Tensor Control Plane, or PTCP, paired with an auditing layer called Tensor Network Quantum Gravity, or TNQG. The PTCP acts as the control plane's core logic. It ingests massive, multimodal streams of infrastructure telemetry and compresses them into a mathematical structure known as a tensor train state. It then maps this high-dimensional state into a predictive graph geometry. To navigate this geometry safely, the system relies on an optimization metric called conditional value at risk, or CVAR. TNQG steps in as the operational topological audit layer. Strict of speculative physics, TNQG is strictly used here to continuously calculate reconstruction residuals, mathematical checks that verify the digital model still matches the physical street. This framework provides a mathematical substrate for joining heterogeneous signals into a coupled state, moving beyond the limitations of single-objective scalar metrics. This chart maps the complete architecture of the mobility digital twin. We begin at the top left with the mobility telemetry block. This initial stage ingests singered operational data, aggregating connected vehicle messages, roadside camera feeds, and real-time signal phases. The architecture converts these raw inputs into a multimodal feature vector, tracking dynamic variables like localized cyber posture, V2X trust scores, and pedestrian density. All of that data flows directly into the next pipeline stage, the PTCP tensor core. Tracking so many intersecting variables creates an incredibly high-dimensional joint state. If a standard computer tried to process every possible combination of cars, pedestrians, and signals in real time, it would trigger an immediate memory explosion. To survive this data load, the architecture relies on the mathematical necessity of tensor train compression. Instead of remembering every discrete data point, these tensor train cores factorize and store the overarching pattern of life state of a corridor. This keeps both memory usage and update costs strictly bounded. By factoring out redundant noise and keeping only the essential geometric structure, this compression makes modeling an entire city's joint cyber-physical state computationally viable. Once compressed, the data enters the third stage, predictive geometry. In the PTCP architecture, the length of an edge on a digital map no longer represents physical distance. An edge mathematically becomes long when it is risky to traverse. That length increases under physical congestion, queue saturation, a low-trust V2X environment, or an active cyber suspect alert. Conversely, an edge is coded as short when it is safe, high capacity, energy efficient, and operationally available. Crucially, the system computes these edge lengths based on forecasted future states, not just a static snapshot of the current graph.
As time moves forward, deformations in this mobility tensor reveal themselves as blocked lanes, sudden pedestrian concentrations, or anomalous network behavior. Because the tensor forecasts these deformations before they fully materialize, the infrastructure can broadcast speed advisories, or candidate detours, before the local sensors on an autonomous vehicle physically encounter the hazard. Mobility control fundamentally becomes a problem of risk-aware path and resource allocation over a predicted, time-varying geometry. To execute actions within that geometry, the framework relies on this core mathematical control equation. The first piece calculates expected loss. But as we established earlier, simply minimizing the average delay across a network leaves the system vulnerable to sudden bottlenecks. That is why the equation adds a conditional value at risk, or CVAR, penalty. CVAR strictly penalizes high tail losses. It forces the system to avoid actions that look efficient on a normal day, but carry a severe mathematical risk of crash exposure, emergency route blockages, or retail queue spillbacks. Letting an unconstrained machine learning model actuate physical public infrastructure is dangerous. That danger is mitigated by the projection operator. This mathematical boundary strictly blocks any recommended action that violates pre-programmed human override parameters or fail-safe rules. If the optimizer suggests an action that violates ADA accessibility requirements, breaks emergency right-of-way, or compromises data privacy, the safe set projects the action back into an allowed state. Autonomous mobility requires verifiable limits, and this projection operator ensures actions are mathematically bounded before they ever influence the physical street. The final safeguard in this architecture is the TNQG auditor, located here on the right. Tensor Network Quantum Gravity is treated here strictly as an operational reconstruction program, serving as a dictionary for reconstructing distances, capacity cuts, and graph curvature directly from tensor network observables. The auditor uses this dictionary to continuously calculate reconstruction residuals, looking for drift. These residuals mathematically flag the exact moment the digital twin's forecast stops matching the actual physical reality of the road or the behavior of the fleet. By catching this mismatch immediately, TNQG prevents silent map drift or adversarial data from corrupting the system, ensuring a safe fallback to baseline operations. This diagram demonstrates how the central control plane interfaces with the wider commercial and public mobility ecosystem. Rather than operating in isolated silos, autonomous vehicle routing, municipal traffic operations, parking availability, and retail drive-thrus are united as interconnected, coupled queues. To answer engineering skepticism, the white paper provides a formal capability superset proof. This proof dictates that when forecast confidence is mathematically inadmissible, the architecture perfectly emulates standard reactive baseline rules. However, when confidence is admissible, it strictly expands upon those baseline capabilities by utilizing the forecasted geometry and CVAR tail risk penalties. The PTCP layer operates as a rigorous capability superset of isolated systems. It allows a city to achieve complex coordination without demanding a monolithic monopoly over private fleet data. Without an interoperable sovereign control plane, the United States risks becoming dependent on a patchwork of opaque, non-interoperable mapping layers and proprietary fleet APIs for public road decision support. This creates a sovereignty risk, where the nation lacks direct control over its own critical mobility data and traffic policy. PTCP and TNQG provide an exportable, standards-aligned reference architecture that keeps public policy, emergency priority, and equity logic under sovereign control. This architecture does not replace vehicle autonomy. It provides the essential, shared, and auditable substrate required to safely operationalize autonomous mobility.